got a team mind.
Okay.
Daniel, I'm gonna have to start bringing extra food to school and hiding it
Some
outside
of
of
the
the
upsells here nationally, so.
Just gonna bring
I have
like
to make a profit somehow. So
random fruit bowls.
All right. So up until this point, we've dealt with function of time. Okay. So things that are dependent upon time. But a whole nother side is position dependent. Okay. So when dealing with time, that has to do with force, momentum, and that side of stuff. Dealing with position as a function of position, that has to do with energy and work. Okay. So there's two different ways to evaluate things. You got the time dependent way, and then you also have the position dependent way. And depending on what you're given, kind of dictates on which route you go. Okay. So the work done by the changing force last year, we did this work is equal to force parallel times distance, and that works great so long as the force is constant. If the force is changing, then we're really hoping it's changing with respects to position, and then we just find the integral of that. Okay. Technically, so this is in one dimension. Technically, that is a more robust definition, which we'll talk about that maybe today.
If not, I can come in tomorrow.
Okay. It's
I need a
okay.
reason to skip my birthday party.
Well, happy birthday.
No, I go with one.
I got it.
Well,
Okay. So recognize that you have different types of work. The net work is the change in kinetic energy. The work done by non-conservative forces, the change in mechanical energy. The work done by conservative forces is equal to the negative change in potential energy. That's just how. That's just for what? Non-conserve? No, that's mine.
I just do NC.
All right. So, how much work did gravity do? Nope. When a rock fell from 10 meters to 2 meters above the ground. Okay. So, the positive direction is considered up. So, what I want to do is you could do this in your head. Go ahead and find the value. Okay. Now what I want to do is I want to set up an integral that hopefully leads to that answer. Okay. So here's what we're doing. Okay. So here's our dependent variable. This is our no. This is our independent variable. This is our dependent variable. Okay. So that's our force. So we want the work done by gravity is equal to, so technically, oops, these are vectors, both of these. Both vectors, yeah. Okay, so you need to take into account direction. So we have a negative force of gravity times a small change in height. Okay. Now, the direction of this is going to be captured by our limits of integration. Okay. We are starting or communicated by which way we're integrating. So we're going from 10, starting, that's our initial, to 2 meters. Does that make sense? Okay. So you have mg dy. Now, watch this little trick here. Oh, I don't want to bring up this trick yet. Sure, I'll bring up this trick. Anything that's constant, you can take out outside of this. Sorry, negative. There's a negative, sorry.
You should keep your upper bound. It's negative mass,
Okay. So, anything that's constant, you can bring outside of the integral. You good with that? So this is essentially finding the integral of 1. Okay. So it's like, right now I'm just trying to teach. I would never do this. This is essentially y to the 0th power. It's not y. Sorry. Sorry, 1 to the 0th power. No. What? Yeah.
He is right.
Yeah, you would never write it like
I would never write it like this, but so you're adding 1 to that and then dividing by 1. So you end up with y going from 2 to 10. Sorry, from 10 to 2. So you get mg times, sorry, negative mg times final minus initial. Okay, which you're changing height.
Dang it! Something was
Okay, so you end up with a positive close to 400.
Ultimate gram.
It's about.
Okay, so positive 392 joules. Should our answer be positive? Okay. And what is our change in potential energy? Negative 392 joules. Everybody good with that? Cool.
Just using y because it's in the vertical direction.
Yep.
No, this is from my
Okay. So that's a constant force. We don't need calculus to do that. Okay. I was just using it just to show you something that we're familiar with. Okay. We will get there. We will get there. You're correct.
Brad, you're not wrong, but I hate it.
All right.
It's not a constant force. As you fall,
I know, Isaac.
physics, man.
We will get there. All right. So, yeah, totally gonna get there. All right, work done by a spring. Hooke's law. Okay. So as you stretch something more and more, the force increases. So force is dependent upon position. Does that make sense?
That's true.
Now, and the negative sign comes from as you stretch it this way, as you pull it in the positive X direction, the force wants to bring it back to its original unstretched length. Does that make sense? So, the work done by the spring is equal to negative kx dx.
Pretty sure it should be Bermuda.
Should be what?
I'm pretty sure there should be some boundings there, but whatever.
That's where they get the 1/2 thing from. That's crazy. Sorry guys, forget I said that one. He's gonna shoot me. I'll let my assistant do this.
Oh my
Don't
goodness.
spoil physics for me. I want to sorry, Smiley.
That's alright.
Do the next one. Physics 2 on Groupon.
Okay. So, we're going to bring out the negative k. And we integrate that.
X squared plus C, but we have
Yeah, it's 1.
Okay. So, I need some room here.
Oh, I see where it comes from. We're seeing. It'll show you.
Okay, so you get 1/2 x squared.
Hey, we have another C here.
Yes, hold on. Now, we're not going to go on to infinity with this. We'll break the spring. Okay, we're not stretching it forever. So, it has, usually, we start with 0 where it's unstretched. And it goes to some final value. X. Okay. Now, that's the simplified. That's the usual. Okay. So we end up with that, but it could start with an initial. It could be, you could like take it from, like if we suspend a string, something vertically, it's already stretched just by gravity. And then we take it and we stretch it more. Okay. How much was the work done by the spring? Well, then you can't just take that because you're squaring this first mathematically, like the order of operations. So you need to do Um, does that make sense?
How does this work if you're going from pulling a spring to pushing?
Great question.
You're gonna find some direction to be positive.
Yep. You make one positive, and then your 0 is going to be at the unstretched, your equilibrium point. Make that 0. And so this is going to be a positive displacement. This is going to be a negative displacement. Okay, and it will work. Okay. So the reason why this is negative work is because as we pull it, we're doing positive work as the external agent, the external force. We're doing positive work, but the spring is doing negative work. What happens to elastic potential energy? Like the spring potential energy. It's increasing. Okay. There's negative work done by the spring. Okay. But a lot of the times we can just simplify things just like what I gave you last year and said potential energy of the spring, or is sometimes called elastic potential energy. It's just given with that expression there. And that's where that came from.
Wait, so is that? Oh, never mind, because you also incorporate gravity. I was going to ask if that's wrong when you have the string already stretched a little bit by gravity, but you're incorporating gravity in there, right? When you add the gravitational potential.
It's not incorporated in this. But if you were doing this and then you wanted to do energy and you stretch, so here's your equilibrium position, and we stretched it. So you have, see, how would you want to do that? You would definitely change your gravitational potential energy. I would make whatever the lowest point you made, I would make that ground 0. And so at this location, it would have gravitational, it would have elastic potential energy, no gravitation. At this point, man, to go hardcore, the unstretched length, that would be no elastic potential energy. So you'd have elastic potential energy here as well, and gravitational potential.
So it's incorporated by including your initial elastic potential.
Mm-hmm.
Gotcha.
Stretching.
Just stretching.
Okay. Good. Oh, and so if you have force as a function of position of a spring, you get that. What is the slope? What does the slope give you? Slope gives you spring constant. This is ignoring the negative sign. Okay. And what does the area under the curve give you? Sorry, not the curve. The area between the graph and the x-axis. And this is how I introduced to you last year this. Okay.
Oh, come on, it's centimeters.
Yeah.
Why not?
Get that out of your house.
Use
You
real
guys-
units.
Every class, can we assume you use meters instead of centimeters?
Oh, ew. Yeah, I don't like this at all.
It would be, well, actually, it'd be less work. Yeah. Are you okay?
So
You like derivative.
Come on, Daniel, do the math in your head.
It is one.
I won't show you my calculator.
-1, but close enough.
Oh, wow. That's crazy.
Yes, I'm aware, Calvin. Yes,
What's the fun?
Are you okay? Yeah, I'm aware. You got 20 points higher than me on the SAT.
well, there is one. Look at that.
It should be negative.
Right. -1 joule. Okay. Now, versus if you found the difference before you squared it, like you couldn't just say 4 centimeters, square 4 centimeters. That would not go well. Okay. Okay. Good with that?
Yes.
Okay. So if we were bringing this back to what you've done, you're used to, you knew how to do this. You would just say, like, there's your 3 centimeters, and there's your 7. This is our initial. This is our final. We would say it would have elastic potential energy or spring potential energy at this location, and it would have it at this location. And then you just subtract the two. Mathematically, you'd end up doing this with what you knew last year.
Why don't we just do the top?
In fact, there's a chance I might have factored
You can.
out the common terms. And
You can, because we know the function. This is something we use all the time, so you know it. There's stuff coming that you haven't seen.
Oh, gotcha.
Like, hey, this is the function of a force. How much work was done? Okay.
Papa John has another molecule. 10 calories per second.
All right.
This changes over time.
That's a
It
water
uses
level.
calories per second.
All right. So, so we have this kinematic equation. Okay. We've seen that. We're used to this. Okay. If acceleration is a function of position, so this is as not multiplied by x, but as a function of position. So I'm bringing this over. You can solve it this way. This is the reason I bring this up. This is just an alternative way, like, on the rubrics, on the free response. This would be an alternative way to solve something where the acceleration was changing as a function of position. I would not recommend going that route. I would do it the work and energy route.
But if you're given acceleration as a
You-
function and one of the two velocities, I'd say go for it.
Well, if you remembered that, that's another. But that's a thing. Okay. So, potential energy graphs. So, if we're graphing potential energy as a function of position, which will happen. I don't know if we did this last year. It might. We might have. Um, the slope of this. Wait a minute. Whoa! Did I switch those?
Yeah.
No, I'm good. If I take this, the negative slope of this is going to be equal to the conservative force, the net conservative force. Okay.
Wait, Mr. Smiley,
Uh-huh.
is this still referring to springs or is this?
In general. Okay, it could be a spring. The spring isn't gonna. That graph isn't gonna look like that for a spring. Potential. I think we'll get there, but I'll use it as a different example.
That's my potential energy.
Okay. So the flip side of this is if you're graphing force as a function of position, you can take the area between the graph and the x-axis equal the work done by your conservative force, which is your negative. And this is what we just did for this. For this graph, the work done by the spring was force as a function of distance. We didn't graph this, but the force as a function of distance would just be
Actually.
okay. Relative close to the Earth's surface. It's really close to the horizontal line. Okay. Now, here's what's gonna mess you up. Is that negative sign. Okay. So it's the slope. It's the negative slope of this.
Maybe the perpendicular slope, at least then it's easy to remember.
Right. But it's not. It's not. It's not a perpendicular. It's just. Okay.
Wait, will you leave that up for 1 more second?
Oh, spoiler alert! I already just did that.
Oh, wait, Mr. Smiley, so is it negative because usually when you take like an integral and like you say like from like on top is 4 to 0, that's like 4, 0, but like since this is like, how do I say this? Like, is it because like your integral it's like kind of flipped which one's on top, which one's bottom? Because like the beginning thing that's the initial.
No, it's blah, 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 blah. I mean, no, that's not true.
Okay, no, you're Daniel's hungry.
All right.
He's really hungry. No one can do that. Daniel, can you take all our tests for us? Wait, no, I'm genuinely curious.
All right. What does Daniel? I think I'm going to answer your question momentarily. I think I think what you're talking about. I think I'll satisfy that here in a second. Okay, so what does the graph look like as we raise something up? For we're graphing potential energy as a function of vertical position. There we go with that. Okay. Now, if we take to find the direction of the conservative force, what are we going to do? We're graphing potential energy as a function of position. Okay, what's this? Is this slope positive or negative? Positive. So the force of gravity is acting in which way? Negative. See how I'm using stuff that we know. Okay. What is the sign of the work done by the conservative force? What's happening to potential energy? It's increasing. Therefore, what's happening to the work? Sorry, not what's happening to. What is the sign of the work done by gravity? Sorry, it's negative. The force is going in the opposite direction of motion. It's negative work. Okay. Man, I used this to figure that out. I wanted to go in this progression. What is the sign of the work done by conservative force? Oh, got it. The work is equal to the force, which is the negative direction, times a positive displacement. Gives you a negative work. Does that make sense? That's the progression I was trying to get to. Okay? And we know that the potential energy is increasing because it's opposite of the work done, the sign of the work done. Good with that? Okay. Ask questions. Next slide's going to be.
Wait, what's the last question?
What happens to the potential energy during this process? Is it increasing or decreasing? As we're going, we're increasing. That's the opposite sign. So delta U is going to be positive. It's going to be opposite of that, the work done.
I understand.
Okay?
I'm probably gonna drown now.
Okay? Now, what is a graph? How would you graph it? Is it doing this? Doing this? It is the same thing.
I fell for this enough last year.
Last year, yep. Okay? Because
I'm definitely gonna miss that one.
okay, because we're not at zero here. We're at some height initially. Zero is down at ground level. Okay, so now again, we find the slope of this to figure out the force. The slope of this graph is still positive, therefore the direction of the force is still negative. Good with that? Okay. The work done, Daniel, this is your question. The work done by the conservative force, you started here and you ended here. Or here. Okay? So your integral, your limits of integration are going to be final minus initial. That takes care of the direction of that. Okay, you're going down. Final minus initial. Also works if you're going up. Final minus initial. That'll give you a positive value for this. Final minus initial will give you negative values. You go that way. Okay. Gravity's still negative. Okay, that get what you're going at. Okay. So the work done is going to end up being positive because this is negative. Okay, so you have a positive work, and then therefore you have a negative change in gravitational potential energy. Get to that? Okay. What about spring force? Okay. What would it look like for a mass oscillating on a horizontal spring? We're graphing potential energy as a function of position 0 being the relaxed, unstretched, uncompressed length.
Yay, right here.
Okay. Good with that? Okay. What is the direction of the force at that location? Tell your neighbor and tell them why.
Okay, let's assume that's positive x. So I just say it's getting pulled right.
So if X is this
Right. Positive x.
It's been negative.
Also true. Also true. Yeah, negative. Sure. That's a good way to think about it. If you want to
And
think
then
about
it goes the other way around.
that's a good way. I don't like that the area under doesn't mean whether it's positive or negative.
Well, the area under, there would be a weird unit, there would be joule meters?
Not in this one, but it.
Yeah.
Okay. So here, that's unstretched and not compressed either. Here, we've been stretched in positive direction. The force from the spring physically is going this way. What's the slope? Is this a positive or negative slope? Positive. Therefore, the direction of force is negative. Okay. Right here, there you see how that works? You have a positive force. Okay. So as we go from here to here, is the work done by the conservative force positive or negative? The work done by the conservative force.
Oh, it's negative.
You're going from here to here. The work done by a conservative force. Okay. So my guess, most of you went this route. You're like, what's happening in potential energy? It's increasing, therefore the work done is going to be negative. Okay. I'm going to try to take you this way. How do you know that? The force is going to be negative, okay, and our dx is a positive value as we're going from here to here, the final minus initial. Okay. If we're going from here to here, what do you think would happen? You have a positive force now. You're going from initial to final negative value minus initial. That's still going to be a negative That's going to be a negative displacement. So don't ever put the negative in there. I'm just trying to teach. Like you do put a positive negative there. You put your positive negatives based upon your limits of integration. You're starting in final. Okay. How are we doing? This would be the work done by the spring as we go from here to here. It's a negative work because we're going in the opposite direction of motion. And this will give you a negative value. Cool with that? Okay. Yep, that's where we'll stop.